All right, let's get right into it. We're going to talk about a brand new way to forecast the weather. But, not the weather down here on Earth. We're looking on 93 million miles away at the sun and a really groundbreaking AI that's learning to predict its every single move.
I mean, seriously, think about that. How do you predict a storm that's happening on a star? The sun isn't just a calm ball of light. It's this churning, chaotic sphere of super hot plasma, and its storms can blast all the way across the solar system. So where would you even begin to guess what it's going to do next?
And this isn't just some abstract science question either. The stakes for us are incredibly high. These solar storms create something called space weather, and if a really big one hits us, it could cause some serious chaos. I'm talking about knocking out satellites, frying our power grids, and messing with all the communication systems we depend on every single day.
Okay, so to predict the future, first you need a really good map of what's happening right now. So let's take a look at how scientists actually create a weather map for our star.
So, the sun takes about 27 days to do one full spin. And as you can see here, from Earth, we can only ever see the part that's facing us. So what scientists do is they take a snapshot of the magnetic field on that visible strip every day. Then, over that full 27-day rotation, they stitch all those little strips together to build one giant, complete, flattened-out map of the entire solar surface.
And this incredible piece of data has a name. It's called a synoptic map. You should really think of it as the ultimate weather chart for the sun. It shows the whole landscape of positive and negative magnetic fields all across the star, and it's the essential starting point for any kind of forecast.
So you've got your map. The big question now is, how do you figure out what the next map is going to look like 27 days from now? Well, for a long time, there's been one main way to do it, but now we've got a brand new challenger in the ring.
So what we have here is a classic showdown. In one corner, you've got the reigning champion, the conventional model. This one is painstakingly programmed with all the known laws of physics that tell us how plasma flows and moves on the sun. And in the other corner, you have the challenger, a new AI model that wasn't taught any physics at all. Instead, it was just shown more than 25 years of these solar maps and was basically told, okay, you figure out the patterns for yourself.
And you can get a sense of just how complex the conventional model is here. It has to juggle all these different forces using really complex equations. You've got differential rotation, that's the fact that the sun's equator spins faster than its poles. Then there's meridional flow, which is this slow, river-like current of plasma. And finally, supergranular diffusion, which is basically the random, bubbling motion you see all over the surface. It's a lot to calculate.
The AI, on the other hand, well, it's totally different. At least on the surface, the process is way simpler. You just feed it the current synoptic map. Its neural network then crunches the numbers, analyzing all the patterns it learned from watching the sun from 1996 to 2023. And then, bam, it spits out its best guess for what that map is going to look like in 27 days. It's simple, it's direct, and it's completely data-driven.
All right, so the stage is set. The old way versus the new way. The big question is, who actually wins this fight? Let's see how they did when they went head-to-head.
Well, the numbers here pretty much tell the story. This chart shows what's called a correlation score, basically how closely the prediction matched reality 27 days later. A score of 1.0 would be a perfect match. As you can see, the AI model scored a 0.71. That's slightly, but very significantly better than the conventional model's 0.68. And, both of them were way better than the persistent model, which is really just a baseline guess that the sun won't change at all.
But here's the thing. The AI didn't just win on points. It also kind of won on style. See, the conventional model has this tendency to smooth things out over time, making its forecasts look a little fuzzy. The AI, though, was way better at keeping all the sharp, fine-grained details of the magnetic field. And this slide right here shows you exactly what I mean. At the top, you have the starting map, and then the actual, real map, 27 days later, the ground truth. Now look at the bottom row. On the left is the conventional model's prediction. See how it looks a little washed out? But on the right, that's the AI's prediction. Just look at how much sharper and more realistic it is. It just looks more like a real observation holding onto those little magnetic features that the other model just blurs away.
And this is where it gets really, really impressive. When the researchers focused only on the strongest magnetic fields, the ones that are most likely to cause dangerous space weather, the AI's accuracy just skyrocketed to a 0.90 correlation score. That's more than double the accuracy of the conventional model for the exact same high-stakes prediction. That's a huge deal. But Of course, no model is perfect. And this AI has one major blind spot, and it's a really critical piece of this whole puzzle.
So this is the AI's key weakness. The model is amazing at predicting how all the existing magnetic spots are going to move and evolve across the sun's surface. But what it can't do is predict the sudden birth of a brand new active region, a sunspot that literally emerges from deep inside the sun. You can see it right here in the red box. A new region popped up on the real map that the AI completely missed because it had absolutely no prior data to work with.
And that leads to a really fascinating question, right? If the AI is just looking at surface patterns, did it really learn the fundamental physics of how our star actually works? Or is it just a really, really clever mimic? To figure this out, the scientists ran this brilliant experiment. They created a totally fake, simplified sun with perfect artificial magnetic spots. That's what you're seeing on the far left. They fed this synthetic data to the AI. And amazingly, the AI's prediction, over on the right, correctly simulated the fundamental laws of solar physics, like that differential rotation we talked about, without ever being taught them. It figured it out. It had learned the rules of the game just by watching.
So, what does all of this actually mean for the future of forecasting space weather? Where do we go from here?
So let's just do a quick recap. We've got this new AI that can forecast the sun's magnetic map a full month ahead. It's beating the old-school physics models in both accuracy and in the fine details. And maybe most amazing of all, it seems to have learned some real solar physics on its own, just from the data. Its one big flaw, though, is that it can't yet see new storms bubbling up from inside the sun.
And the reason this matters so much is that these more accurate 27-day maps can be used as a way better starting point for other, even more complex models, the ones that predicts things like solar wind and coronal mass ejections. This could be the key to pushing our reliable space weather forecasts from just a few days out to maybe a month or even more.
And this all brings us to one final, really big picture idea to chew on. Just think about this for a second. This AI wasn't handed a bunch of physics equations. It figured out the rules just by observing. So if an AI can learn the physics of a star just by watching it, what's next? What other incredibly complex systems could we turn it loose on? Climate patterns? The stock market? The intricate dance of proteins happening inside our own cells? It feels like we're standing on the edge of a fascinating new frontier for prediction.